So when it comes to requesting the website, we can go about it in a few different ways. And through the evolution of the framework, they have made it easier and easier to do web request and response because, well, frankly, that's the way everything works now. So I'm going to show you both versions. One utilizes a stream and one does not. So I'm going to give you kind of a high-level view of it, and then I'm going to give you the low-level view so that you really can see what's happening. So I'm going to call URL high level, and I will pass in our URL. So I'm going to generate a function that does that work. And actually, it's going to return output text. So if I jump into that function definition, I now have this function that takes in the URL or URI, returns a string, and I have to put a body. So the quick and dirty implementation is under system.net, and then we want to use the web client. Okay? The client has what's called download. We have download data, download file, download string is the one I want. And you'll see in here it has two overloads. One takes a string address and one takes a URI. So I'm going to pass in our URL in there. And I'm just going to do a straight return. Typically, you'd probably do things like a try catch block, make sure that it's valid.
Just return the HTTP or the HTML of the document, is that right?
Yes.
Okay.
So this download string returns a string. We're returning that string. The string is the HTML markup of that page that we're requesting.
Okay.
So we'll go ahead and just throw that. I'll put a breakpoint in case we have an issue. So that's the high level implementation. I mean, you can't get any simpler than that probably. So if we run that, so we'll just do Google, right? Oh. So we capture the response, These are all the steps that we're going to do in the low level. So let's adjust this. Output text equals call URL low level. Generate that function, comment that out, and then console.write line output text. All right, let's try it again. Oh, wait, one more. Console.read. And there's the HTML. Isn't it beautiful? So if we run it again, pull up Google. View source. Just cruise to the bottom. Let's see here. Huh. It actually sent different code to our app than it did the browser. So if you look down here at the bottom, you have google.timers.load, TP, blah, 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 time, whole bunch of squiggle, script, div body. Here it says window.setTimeout google.j.xi.0, and then that's the end of it. So it actually sent us different markup.
When you went to the Google, it changed the URL in the bar to something different.
When I entered Google?
Yeah, see.
Oh, okay.
Extra stuff.
So that could be part of it. It could, that may be missing the redirect. So paste. There it is. Nope, still different. Still different. Now, if we wanted to, we could take all of this. So let's use this as a good example then. System.io.file.write. So we can write all lines. I don't know what my desktop is actually pointing to. Copy, paste. At symbol does it makes it so you don't have to do the double escapes. Otherwise, you have to go / / / like that to type in a path / mygoogle.htm. So I'm gonna go ahead and take our output text and write that out to a file.
You know, escape for my Google.
Yes, that, but it's complaining about, let me try a different overload, write all text. Oh, it needs comma. Oh, no, it doesn't. Okay. Write all lines wanted a collection of lines. Write all text just takes one string. So it was wanting multiple strings in the other one. So if you run that now, we should have that page, which is actually very different than that page.
Is it because it doesn't have the CSS?
DGC's website.
Okay. Delete that. So we'll do.
Is it because you're not getting the CSS as well? They might be putting it in a separate file.
No, well, yes, everything's coming in a separate file. The reason it's coming up that way has to do with each browser has a signature. The signature tells the server what browser you're dealing with. So your phones, the browser actually has markup detail that says what kind of browser it is, what device it is. Sometimes it even pushes like resolution data. And our client's header data is basically not saying I'm Chrome. It probably says I'm some version of Internet Explorer that's probably like IE6. Because of that, Google is responding and saying, well, I'm not going to send you the latest and greatest version of Google. I'm going to send you an older version of Google's homepage that's compatible with that device.
Could you make it think you were Chrome?
I could. I don't know off the top of my head all the changes I would have to make. So
Web browser.
Huh?
You'd have to make it run in a web browser, right?
No, you can actually modify the
Or a web client.
you have to modify the user agent that's in the header. Do I have Fiddler on here? Alright. I will, if you're interested, I will do it after I finish. I'll walk you through it and you can see the header data and all that stuff. So you want to do UC. Alright, so there's UC's homepage. Come on.
So like, why didn't you have to close the file or anything to make sure that it saves? Like,
The reason
like Java was it do like .close or something like that?
you always have to close the file because
Yeah.
what happens is that the file is a resource that can be locked.
Okay.
So without closing the file or closing the stream, the resource becomes locked, and basically your application owns it.
Okay.
So if it's a file that multiple people are writing to, let's say,
Yeah.
until you close it, no other person or program can write to that file. You take exclusive ownership and exclusive rights to it. Have you ever run the scenario where you try to delete a file and it says this file is in use?
Yeah.
That's because the program using it hasn't called closed.
Okay.
So think of it like a library. It's kind of like a checkout process.
All right.
And there's actually different modes of checkout. You can do an exclusive checkout, which is the default that says, I own this file, no one else is allowed to touch it. And that actually gets written to the file system in the file system metadata. It says this is checked out by this program and no one can touch it. You can do shared checkouts. So let's say you're only going to read the file. You can say, I'm going to read from it. Other people are allowed to read and write from it as well.
Okay.
Or you can do an exclusive write, or you can do a shared write, which is interesting. Basically, you say, I'm going to write to it, but other people can read and write from it while I'm writing to it. Those get a little kind of funny. But you can do it. All right, so this is UC's page with no CSS. Let me try real fast, see if I can turn off the style sheet. Disable JavaScript. Yeah, there's no easy way to do that. Okay, I won't spend time. There used to be a little add-on for Firefox that you could go in and disable the style sheets. I used to actually use it even in the dev tools for Chrome, but it's not there anymore. So you could strip it off so you get side by sides. So anybody know why this one has no CSS?
Are they separate file, I guess? Or, because you could put the CSS with the HTML, you can make a separate file for it.
Correct.
Link to the file.
Yeah.
I was gonna say it's looking for a file that's not there on the computer because it's probably shortcutted on the website.
Right. So within the markup, the link tags, that's the icon, link, style sheet link.
Because they're using relative URL.
Correct. So think about the process your browser goes through. And I haven't even gotten into the details of actually using streams yet. Your browser actually goes out, the first thing it does is it requests this content, this text. It then has to go through and find every tag, identify it, categorize it, and determine and calculate how it should be rendered out on the page. How big is the image supposed to be? Where is it located? Where's the text? How does it wrap? How does it fit within the window? All of that has to be determined. Plus, it has to identify every additional resource, every image, style sheet, external JavaScript, fav icon that's referenced within that HTML, and it has to make a subsequent request out to the server to get that content. So for every element you add to your page, every graphic, every style sheet, external sheet that you add, that becomes another request that the browser has to make. Now typically it's not a problem anymore because of how fast our devices are and how fast our internet is. You can go out and request 100, 200 kilobyte images, and that doesn't take any time. But when you're on old, slow mobile devices, or back when you were using dial-up, that was a big deal. And when you talk about page speed and page load time in the user experience, that becomes a big deal. If you actually look at something like Gmail and the number of images and elements that are on that page, you really have to start to calculate how much time does it take for all that to load. How just all of those aspects of getting a page to load. Something that I always find fun to look at in Chrome is if you pull up these DevTools and you go to Network, I'm going to clear it, get that out of the way. I'm just going to refresh the page. Every one of these elements listed here is one of the items or components that the browser had to go out and make a subsequent request for. Now you'll notice here you have certain elements that have these gray bars in front of them. You have other elements that don't. The gray bar is identifying, or I'm sorry, not the gray bar, but the white bars. The gray bar is a stalled state, and that typically occurs when you have large requests that are blocking. A browser under the HTTP 1.1 standard can only make 2 concurrent requests to a web server. So if 2 requests are made and the server's waiting for, or I'm sorry, the browser's waiting for one or both of them to respond, it actually has to wait, according to the rules, for all that content to come back before it can make another request. So every stall that occurs here, and we can probably do it by start time. See, stalled, and then it has to go through all these steps. A stall, DNS lookup, initializing the connection, sending the request, waiting for a response, actually downloading the content, and all of that happens to get that HTML content in 21.62 milliseconds. Then once it's downloaded the page, it has to parse through it and identify all the other resources. So it has to go through, get the connection, download the CSS file, download 1, 2, 3, 4 JavaScript files. And we haven't even parsed it or processed it. It's just downloading the content. We've got some more CSS, some more JavaScript, some more CSS. We have some pictures. Got to download 1, 2, 3, 4. Well, you get the picture. Here's a font, another JavaScript, another CSS, more images, more JavaScript, more CSS, more images. So there was 47 requests total. 30.5 kilobytes were transferred. It took 1.61 seconds. The load took 1.59 seconds, and then the what's called the DOM content loaded took 1.28 seconds. So it was running in tandem. So it was actually the amount of time to download and then process all the content and put it on the page. So I don't know how many of you knew about all of that prior. So that's how your browser works. So if you were to actually build from the ground up a whole new browser, this is all the mechanics that your browser does for you. So when you write an HTML page, you're not even probably typically thinking about all of this that goes into the browser doing its part. Another one that's interesting to see, we'll do Google again. 19 requests. And you see how there's very few stalls? And a lot of it's being pulled from cache, so that's why. Let me do this. Control F5. And there's still very few stalls. And that page loaded. Oh, it's still loading. So you have very few stalls, and then you have some of these outstanding requests where it's actually doing calls after the fact when the page loads. So something fun to dig into. So the way that the browser typically handles it is it handles it using that low-level processing.